Hello all. Thank you for joining our today's webinar. It's part of our project, the Collaborative Innovation in 3D VLSI Reliability. Our today webinar is about the reliability assessment in emerging technologies and what we can do beyond 2.5D and 3D chiplets. To start, I think to give you a bit brief of the agenda, I will do the introduction, then I will pass the floor to our colleague from University of Amsterdam for the estimation for core failure resilient of multi-core processor. Then we have the talk from Dr. Tahani Aladwani from University of Glasgow regarding AI-driven thermal prediction for enhanced reliability in 3D hybrid memory chiplets. And then we have the final talk from Professor Alberto Garcia-Ortiz from University of Bremen regarding coding approaches for increasing reliability and energy efficiency of 3D technologies, following by a Q&A section where you can post questions in the QA of the webinar. Now, starting for us, we say that there has never been a better time for semiconductor, especially in the EU Union. And we have to consider this cycle that is totally interconnected, and we need to enhance it in all over the different approaches. So one of the basic problems is that we need more training material and open source tools that they're really a big need, especially for the EU, which is not having so much research on this topic, in order to create more R&D, since we have now big data, IoT, and trillions of edge sensor, deep learning, we have exascale supercomputing, and it's like now the fourth horse rider of the silicon apocalypse are now here, because you cannot get more performance from a single chip. You cannot have great area, great power, and great timing. So we have to go beyond CMOS with emerging architecture, emerging devices and processes, and emerging materials in order to meet the efficiency and the performance need. And of course, we have to expand the silicon application. Right now, silicon is everywhere. It's anything you name it, it has a simple processor and microcontroller. So we have to meet all these different aspects. And of course, this will create also revenue, because the EDA revenue semiconductors continue rising and rising. So for us in COIN-3D project, we have different scientific activities working from circuit layer. We have created open source methodologies for 3D IC design. We have implemented some machine learning methods for interconnect optimization and reliability assessment in 3D chiplets. We're working on system layer also, on the more architectural. We try to create this hot proton tool and implement scheduler for 3D level simulation, soft and hardware modeling at the architectural level, and create macro models across the 3D stacking. Which all of these technologies are backed with numerical and model order reduction solvers, machine and deep learning methodologies, and several processing models for 3D stacked architectures. And of course, part of all of what we're doing and what we're doing also in the research, we try to promote them in different webinars, courses, and summer schools that we create in COIN-3D context. So COIN-3D has a great goal on research and knowledge exchange in 3D VLSI domain between the University of Thessaly and other advanced partners from Europe. So we have already delivered 2 webinars regarding machine learning application in EDA for chiplet reliability, which is on our YouTube channel, and the custom tool development strategies for chiplet reliability also, which again you can visit it on our YouTube channel. So today is our final webinar, our final technical webinar. We will have some dissemination webinar as well, but it's the final of this series. With that, I will pass the floor to Anuj for his talk about lifetime estimation for core failure resilient multi-core processors. So I think, Anush, the floor is yours.
Thank you. Let me. So let me start by telling a little bit about myself. So my name is Anuj Pathania. I'm an assistant professor here at University of Amsterdam, and I started here a little more than 5 years ago. I am originally from New Delhi, India, and I did my PhD from Karlsruhe Institute of Technology in Germany. And my area of expertise is low power design, embedded systems, and electronic design automations or EDA. So today I'm going to talk about how to model the mean time to failure for multi-core processors that are resistant to core failure, which basically means that they can still survive if one of the cores or many of its cores still dies out and so on. So this is how a typical multi-core processor looks like. So you have a series of cores, and each core has its own individual memory, and and then these cores communicate using a shared memory, which is shared by one or more cores. And then the communication happens over a bus interface, and then the whole chip itself, the multi-core chip, communicates with other chiplets or other components using a off-chip component interconnect. So the idea behind core failure and resistant multi-core is that the the cores, they are allowed to fail. So generally, if a core fails at runtime for a normal multi-core processor, then the whole chip itself dies because the hardware and the firmware cannot handle a core not working properly. So either all the cores work, or if or the chip dies. But this technology, the core failure resistant, allows the chip to survive one or multiple core failures, and the cores which are still functional continues to work even if their fellow cores are no longer working. This technology is especially useful in server scenarios where cores are constantly operating at very high utilization, and there's also a lot of heat that is being generated, and because of the temperature, the core failure is very common. Some of these multi-core processors also have the ability to handle the failure of memory banks, for example, in the last level cache. But this is something which we have not explored yet. So here we will focus on mostly on the failure of the cores themselves, not the impact of what would happen when the memory banks start to fail and so on. So in for this work, we took uh, applications which were given in form of a directed acyclic graph or a DAG, and then this DAG is scheduled to be executed on a multi-core processor, and then, for example, then the first core fails, then the whole system realigns itself, and the remaining cores must pick up the load of the first core failure and continue to provide the performance, but at a higher utilization, at a higher temperature, and so on. And then the process repeats till all the cores fail and there's no longer a surviving core. And because core failure is a random process, you have to simulate the whole failure of the cores, which would happen over many years. But in simulation, we do it kind of fast. You have to do Monte Carlo simulations several times to obtain the mean time to failure for this kind of processor. So, so here is a simple example where we have a dual core, uh, core failure resistant multi-core, and there are two cores and they are working, and based on their initial working profile and what kind of workload they have experienced in their history and what kind of temperature and the core have experienced, they have different level of reliability. So these reliabilities are generally measured in what we call the R value, when R value basically is a value between 0 and 1, which tells you that how likely it is that the core would fail in the next instant. So if an R value is 100%, then there is very little chance that the core will fail. Whereas if the core has a value of zero, then a value of zero, then that means that core is very old and could fail anytime. But let's say if it has a R value of 0.5, then basically it means that the core can, there's a 50% chance that in the next cycle, the core would fail. Because core failing is a random process, but when we are doing simulations, we do not have real cores that are failing. So we basically assume that like if the R value drops below a certain value, then the core is dead, or we can assume that we run a random number generator and see if the number generator says, okay, the probability is higher that the core would fail, then we fail the core even if the R value is very high, and the core can similarly survive by the randomness even if the R value is low. So in this particular example, what we are seeing is that we have the reliability curve of a dual core processor, and one core has more aged age than the other core because it has a steeper the curve for the R reliability curve. So now the two things can happen in this multi-core processor. One thing is that in the next instance, when we are simulating, an older core fails first, or then on the other side, what could happen is that a younger core fails first just by the randomness simulations. So we have to cater for both of these cases. But but generally, what is assumed in most of the works or the reliability simulation is as soon as the first core fails, what would happen is the simulation stops and you report the time to failure. But in our case, that is not the case because we have the core failure resistance capabilities, which allows us to prevent the multi-core from completely dying. So we have to model the lifetime of such a chip. So this is how the fault distribution curve for the surviving core changes. So let's say in our case, the young core, the old core fails. So the core which is younger need to take over the load. So the reliability curve shifts for that particular core middle of its execution from the old red one to the new blue one. So if you want to model the curve for the whole lifetime of this chip, we have to create a hybrid curve where blue one was the time where there were two cores in the system, and the red one is now the time where there is one core in the system. So this is how the eventual reliability curve for that surviving core would look like. And the curve will actually be much steeper because the workload has to be picked up, and that would mean that there would be more heat generated on this processor, which will accelerate its aging because it's not taking the full load of the system. And to do this, we created a framework called Slicer, which is a framework built on the Hot Sniper tool, which also George talked about with Hot Proton. So they are related. So basically, we used trace-based simulations in our Slicer framework based on this Hot Sniper tool, where we have a scheduler which reschedules the workload, and then we have thermal simulations, and then we have an aging simulator, and all of this work. And user provides with software description, hardware description, SLAs, and scheduling policy, and the framework can give you the mean time to failure. So what we did was that we didn't propose our own reliability scheduling algorithm. There are several reliability scheduling algorithms already out there. So we gave the same input in terms of this hardware software description and the deadlines, and we saw how good these reliability scheduling algorithms are. And our tools was able to say that, like, for example, this DWDS algorithm is much better at providing higher reliability within the same performance constraint than other ones in most of the cases for most of the benchmarks. So this is the final slide. And here I want to just give you quickly what things are happening. For example, what is happening. So in the first case, you could see that all the cores are active, and the tasks are relatively equally distributed. And then because the core one was more overloaded by the scheduler, it is the first one to die. And then what happens is that the tasks now are shifted more to the other cores. But the important point to note is that, like, even if a core dies, our simulation takes into account the fact that the core is still acting as a heat sink and can still survive, can still provide cooling effect to the neighboring cores, even though now it's not active. Especially now that it's not active and it's dead, it is in even a better heat sink than it was in the past case. So it would help the surviving cores a little bit with the temperature and so on, especially the neighboring cores. But eventually, because now the existing cores have to take more and more and more load, they start to become hotter and hotter, as you can see in the different steps, what is happening in the simulation. And eventually you reach a point that you don't have any more cores, and the core failures becomes even more faster process because of the higher temperature and so on. And then when you simulate this hundreds and thousands of times, you can kind of get an estimation for the mean time to failure for core failure resistant multi-core chip. And with this, I would like to end, but I think the Q&A would be in the end. So I would hand back the floor back to George.
Exactly. Thank you, Anuj. And I think I just pass the floor to Tahani for the second talk. Tahani, I think the floor is yours. Yes.
Hi. Can you see my screen?
Yes. Perfect.
Okay, perfect. Hello, everyone. My name is Tahani. I'm a postdoc at the University of Glasgow. My field of expertise is AI and data-driven solutions. Today, I'm gonna to talk about Today I'm gonna to talk about AI-driven thermal prediction for enhanced reliability in a 3D high bandwidth memory chiplets.
Tahani, I think you're not sharing. Sorry. We cannot see your share screen.
You can see my screen now?
Not yet.
Just 1 second. You can see it now.
Yes,
Can you see
yes,
it now?
yes.
Yes, perfect. Sorry about this. Yeah, so first, why 3D high bandwidth memory matter for modern AI accelerators? When we talk about modern high-end AI accelerators, such as GPU or AI accelerators, this kind of technology heavily rely on 3D high bandwidth memory to meet the bandwidth and energy demand for high performance computing, data-centric application, and advanced AI workload. What kind of the advantages that high bandwidth memory can provide for these kind of advanced applications? First, high bandwidth memory provide with vertical stacked multiplied DRAM die in 3D stack or 3D structure, and also provide with low latency, low power consumption, better energy efficiency, and higher capacity. So in general, we can say high bandwidth memory is a key technology that enable advanced models like large language model deployment and development. And it's also important for any AI or deep learning model that must process very large amount of data as fast as possible. So when we talk about the high bandwidth memory architecture, it's not a new kind of memory. It's about how we deploy the DRAMs or memories in the system. So, for example, when we talk about this stack of memories, we can see this as a four high bandwidth memory from the top to the bottom. At the first, we will have from the bottom substrate, a silicon substrate at the bottom. Then we will have 4 chips or memories. These chips or memory include through silicon vias structures in each chip or each memories. And also these kind of memories will be connected with each other through bonding layers. And at the top, we will have the heat sink or cooling conditions to have like air cooling, liquid cooling, or physical change cooling. This is for high bandwidth memory, but we could have 8 layers or of memories, or 4, 2, 1, or more. So when we talk about the high bandwidth memory stack, it's considered more complicated than the DRAM chips or the traditional methods, because we deal with 3D architecture, and the connection is sophistications. So in general, we can say it's important to have thermal management to ensure high bandwidth memory technology can operate with the safe thermal limit and thereby maintain high performance in the demanding computing environments. Also, when we talk about thermal management challenges in the high bandwidth memory, we will have the problem is the high power density with stacked chips, especially in the middle layers, that can creating a localized hotspot, which can causing something called thermal stress in the materials and perform degradation and reduce reliability if it is not controlled. Also, we could have another problem, which is the thermal conductivity of the material used in building TSV. It's often insufficient and resulting in building up heat that affect the whole system performance. So these challenges require efficient thermal design solutions that require the integration of advanced predictive technology to ensure optimal thermal performance. Actually, there are many classic optimization techniques have been used to optimize thermal performance for high density chip stacks. But these methods are not enough. Why this method they are not enough, we will see now. First, we will talk about the traditional finite element analysis. This is considered very good and very accurate for simulation heat conditions. But it's become computationally intensive when we talk about large and complex system like 3D stacks. So also it's considered very slow when we talk about the simulation. We will try to explore and optimize different solution space. There is another method can be used as well, which is faster simplified model. This kind of models tends to rely on simplify the model to do some task, but actually it's considered lower accuracy, especially when we talk about 3D structure and TSV configuration. Accordingly, we can say in general, it's hard to optimize thermal performance for high density chip stack, and also the hotspot and reliability issue may be missed until later in the design flow. So we will talk about the data-driven and AI solution. Data-driven and AI solution is not a new thing. It's applied in different fields, and we will see how we can use it here for optimization goals. Data-driven with the neural network can learn from the finite element analysis data to optimize, to compute a complex non-linear thermal behavior and hotspot position with high accuracy. It also can provide with fast prediction to enable thermal optimization of advanced high perform memory architectural. Based on this paper that called Neural Network Surrogate Model for Junction Temperature and Hotspot Position in 3D Multi-Layer High Bandwidth Memory Chiplet under varying thermal conditions, we will show how data-driven neural network can act as a thermal prediction model for 3D high bandwidth memory structure under varying operating and cooling conditions. First, when we talk apply AI-driven solution or deep learning models for solving such kind of problems, we need to have data. And the best source to have the data, it will be the thermal simulations, such as finite element analysis to build a 3D hyperparameter architectural. Then we will use this we will do kind of data preprocessing for the thermal simulation and for the neural network to work on this data. Then we will see the neural network architectural and training. Then how the prediction temperature and position work. First, when we talk about the data source, it will be from the thermal simulation. According to the paper that we talked about, they used INSYS to run many 3D thermal simulation of high bandwidth memory stack and detailed 3D high bandwidth memory models like substrate, chips, TSV regions, and the heat sinks. And also they used thermal solver computes the full temperature distribution, include the junction temperature and the hotspots. Actually, as we said, we need to have like thousands or 10,000s of samples. So they used Python script to make this process automated to generate samples or simulation forms from the INSYS apps. So for every iteration with the Python, they try to switch the high bandwidth memory structure and also the power, chip thickness, TSV, material of thermal conductivity, and HTC. So then they launched the simulation automatically. After that, they will get the expected or extracted result as a junction temperature and hotspot positions. It will be something like that. This like the Python script with the INSYS. They will iterate through a different number of high bandwidth memory layers like 1, 2, 4, and 8. And also the layer thickness, it will be changed from 10, 30, 50 with maximum number 700 to 720. Then also the materials properties and TSV pattern, it will be changed with each round, the power value, cooling conditions. All of these simulation, it will be used to produce large data set to be used for the neural network model training. So for each of this combination, one thermal simulation, it will be considered one data point for the neural network training. For example, here, each of this simulation, it will go through a neural network to predict two output junction temperature and hotspot positions. For the data processing, we will have two kinds of data processing. Data processing for the simulation itself and data processing for neural network. For the data processing for the simulation, in general, when we talk about all the possible combination of high bandwidth memory structure, the number of cases it's exploded as we add more layers. The number of cases or the combinations can arrive for million or even billion of simulation, which is impossible to simulate all of these cases. For example, when we talk about 8-layer model or architecture, for each of these layers, we have 4 group of parameters. The first chip thickness, we will have the logic and 7 memory layers. In general, we will have 8 layers. And for the TSV or chip thermal conductivity, we will have also 1 logic layer and 7 memory layers. In general, we will have 8. Also, for the power, we will have 1 logic layer and 8 memory chips. In general, we will have 9 layers. For the cooling, we could have top and bottom surface, 2 sides. And in general, we will have 27 parameters, which and all of these parameters, it will be with 3 possible values, low, medium, and high. In general, we will have like 3 out of 3 power to 27, which almost 7.6 million trillion combination. And it's not easy to simulate such a number in CIS. So we need to reduce this number, but with an efficient way, and also to include all the important combinations. There is a method called sampling method. It's called partial Latin hypercap sampling. This method, it can go through all of these combinations and select the best, like according to the percentages that we define. It can select like few thousand of samples rather than trillion or billion that can cover all the parameter spaces. After removing the non-physical result, we could have 30,000 simulation. It's become a nice number for building neural network. And also having like 1,000 simulation, it's reduced the simulation time and still provide us with all the required informations. After the simulation, we expect to use this data for training a neural network model. But actually, we need to do some pre-processing to make the data fit very well for the model. For example, we need to do some normalization for the input data to have all the data in specific range between 0 to 1 or between -1 to 1, rather than having like a huge difference between the values. So here they use the normalization for thickness, power, HTC, temperature, and other factors to have it like in the same range. And also, when we talk about different structure of layers, like 1, 2, 4, 8 layers, that means we will have different number of dimensions. If we have 8 layers, we will have different dimensions number compared to having 1 or 2 layers. So they did something called placeholder to fill these places with -1 to have all the dimensions equal for 8 layers, 4 layers, 2, and 1. Then, as usual machine learning, deep learning models, we will split the data for training. The training, it can be like 80%, most of the data used to the training, and 20% or less for the testing the neural network. According to the training process itself, we could have two kind of architectural to train deep learning model that can predict both junction temperature and the hotspot position. First, architectural, something called one neural network, two outputs. For this kind of neural network, we could have single neural network that can predict two output structure. This kind of architectural consider very nice to enhance computational efficiency and reduce redundancy parameters. And for more complicated scenarios or to get more accurate results, we could need to use two neural network, one neural network for junction temperature and another neural network for the hotspot position. In general, when we have two neural network, we expect to have the junction temperature neural network to be more smaller than the neural network used to the hotspot position because the temperature it's more easy and more smoother, and also it can be solved by using linear activation. But for the hotspot position, we could need to use more layers and using non-linear output activations. This is the first architectural. As we can see, every combination, it can be as a one input for the neural network. And for one neural network and two outputs, as we can see here, the first branch, it will be the temperature. It will be finished its training after the first hidden layer, because we don't need to make this go deeper, because it's very simple and it can be predicted by one layer. And for the second branch, which is the position, it's need to will train or more deeper trainer, so it will go through 4 layers, and both of them will go through the mean square errors. As we can see here, for the temperature, we will measure the mean square error, and also for the position, we will compute the mean square error. And for the position, we can multiply with specific factor like 10 or any numbers as a way to reflect the importance of this value. For the two neural network architectural, we could have one simpler neural network for the temperature with the 3 layers, and one with more layers to the position. And also we can apply the dropout here to avoid the overfitting. And the advantages of this network, it can give better accuracy. So according to the performed comparison for two neural network and two outputs, it's give better temperature, because the temperature has like different model with more layers, and it can give like some better result. But for the position, it's not it's give like worse result than the one neural network two output. So for the one neural network and two outputs, it's give better position prediction, but it's like a little bit lower in the temperature. According to the comparison or the result comparing to the simulation, which is the accurate result or the main baseline, this figure show one high bandwidth memory with 1 layer, and high bandwidth memory with 2 layer, 4 layer, 8 layers. And for the blue circle, we can this is the simulation data, and for the star, it's the prediction. As we can see here, the prediction by the neural network and the simulation, it's almost the same, and the model can predict this temperature and position with high accuracy, similar for what we can get from the simulation with the faster implementation. So, and also here, they try to measure the generalization of the model according to unseen data. So for the blue circle here, it's the prediction, and the green star here, it's the simulation. As we can see here, the model prediction, it's very close to the simulation, even for the unseen data, which means the model can generalize very well for unseen cases. In general, we can say we can build a data-driven neural network model to predict the junction temperature and the hotspot position from the key design parameters like layer thickness, TSV conductivity, and power HTC. So in general, this neural network model, it can give like about 98.4 accuracy compared to fine element analysis, which is considered very huge accuracy with a few like second or few minutes to have this model done. And also this kind of model, it can generalize very well for only unseen data. So also this is considered very helpful because it's very fast. So this is the final slide. Thank you very much.
Thank you, Tahani, for the talk and the presentation. So I think I will give the floor to Alberto. I think everybody who has a question during the talks, you can just put it on the Q&A section and then we can discuss it at the end. So Alberto, I think the floor is yours.
So my goal in this presentation is to try to discuss if there are some... One second, please. If we can try to develop some techniques that will allow us to reduce the energy consumption and therefore to improve the energy efficiency by doing coding in 3D technologies. I see that there is a lot of echo.
Yes, for somehow. I think, Tahani, if you can close your mic. Now, maybe it's better.
Perfect. So shortly about me, my name is Alberto Garcia-Ortiz. I'm professor in the University of Bremen. And you see that I have a very strong accent. I'm coming originally from Spain. The work that I want to present today has been done in collaboration with the University of Magdeburg. And we have this collaboration in two directions. One is in the direction of low power coding for more classical technologies, like, for example, the chiplet technology or the TSV technology that we have been seeing in the previous presentations. Part of this result, we can find it in our book about 3D interconnects. Nevertheless, what I would like to focus today is in the goals of coding, but when we try to move in newer technologies, and in particular in monolithic technologies. So in short, the goal of our presentation is to try to answer the question whether we can use low power coding techniques to try to improve the reliability and the energy efficiency of the 3D technologies. So that means if we can reduce the power consumption. We want to target monolithic 3D technologies that, as we will see in the next slide, are especially challenging because they are strongly heterogeneous. So the different tiers that we have are going to come fundamentally from different technologies. And because of that, the kind of drivers and the parasitics that we have for the wires in the different tiers are going to be completely. In order to analyze the energy consumption, we are fundamentally going to try to work in two directions. The first is the energy modeling. So what we are going to do is to try to develop one model that is able to predict the power consumption when we transmit information through the wires in a monolithic approach, with the special point that we want to take into account that when we are sending data in these heterogeneous architectures, the fact that the speed of movement of the transition is not the same in all the lines changes actually the power consumption. it is not only that the power consumption depends on the particular pattern that we have to switch in, it is also that the alignment of the signals plays a major role. Once we have able to model the energy consumption in monolithic 3D technologies, what we would like to propose is some low power coding approaches that can be used to reduce the power consumption. The key challenge in this third point is that since we are addressing monolithic technologies with the amount of wiring of vertical interconnect that we have is huge, the overhead that we can have for the low power coding has to be extremely simple. What we are going to develop is a very small module fundamentally based in a set of XOR gates, which is able to reduce most of the, let's say, redundancy that we have in the data, just with a cost which is fundamentally proportional to the number of lines, so extremely small. So let's start with the motivation, why to try to address coding for these fine pitch 3D technologies. If we analyze the landscape of 3D technologies, we will see that classically we have been working in 3D technologies that have a very sparse, let's say, number of tiers. For example, in the previous presentation, we were learning how to handle temperature effect in the stacking of different chips. Fundamentally, at that, the kind of granularity that we have for the vertical interconnect is the one of the TSVs, and because of that, far below this limit of 5 micrometers. If we want to develop 3 technologies that allow us to separate, to disaggregate the part of a system on chip, separating at the level of the gate between the different technologies, then we are going to need a kind of density for the vertical interconnect, a kind of pitch, which is below 5 micrometers. Today, the candidate technologies to try to have this very dense 3D interconnect are on the one side, the electric bonding with VLRs or hybrid bonding. With that, we can get close to 400 nanometers in terms of interconnect. If we want to move even further in terms of interconnect, our next candidate is monolithic 3D. And actually, this is going to be the target for my presentation today. If we try to understand a little bit more generally how monolithic 3D works, you will see that fundamentally we are processing one tier here, what we have in the lower part with aluminum in terms of the lower interconnect, MP between 1, 3, and maybe middle interconnect, maybe another three layers. Once we have implemented this low technology with the layers, then we would like to add another tier, and on top of that, to continue with the metallization. The advantage of this kind of technology is that by doing this, let's say, interconnect in terms of tiers implemented sequentially, we can get a very, very high density in terms of vertical interconnect. Nevertheless, this kind of technology had some fundamental, let's say, limitation. The first one is that when we produce the devices, the transistors that we have in the upper layer, the temperature profile that we are using is affecting negatively the chip that we have produced in the lower part. Because of that, typically we have to use technologies which are limiting dramatically the temperature during the processing of the upper tier. These, in the praxis, means that the kind of transistor that we have in the upper tier fundamentally are slower, are of a lower quality than the transistor that we have in the bottom tier. We can try to model that just assuming that the two tiers have technologies which are, let's say, different. The second fundamental limitation is that since we want to connect with a fine pitch the low tier with the upper one, we see that the amount of wires that we can use there is actually much more limited. Even worse, since once we have implemented the metallization in the bottom tier, we want to implement the upper one. The temperature that we have to use should not degrade the metallization down. And because of that, we are really limited in the amount of materials that you can use for the bottom technology. This fundamentally means that the resistance that we are going to have in this bottom tier, that the quality of the interconnect that we are going to have in the bottom tier is actually worse than the interconnect that we have in the upper tiers. So if we try to, let's say, summarize this, the fundamental message is that in monolithic 3D, we have a very highly heterogeneous scenario, where in the bottom tier, we have fast transistors with slow wires and limited wires, while in the upper tier, we have slow transistors, but a lot of interconnect and very fast wires. In this slide, we have just a short idea about how is the implementation of the monolithic 3D. Fundamentally, we are starting with one wafer where we implement the transistors, then the metal interconnect. Once this bottom tier is implemented, we can somehow glue another tier using a technology which is very, very similar to the process that we were using for the wafer-to-wafer connection with hybrid bonding. After that, we can thin the upper tier, and fundamentally, we will get the layer where we can implement the transistor. In the next step, we will start implementing the transistors of the upper tier. Then with the help of MIVs, we can add some interconnect between the upper tiers and the lower tiers. After that, we can continue the implementation of the metal layers in the upper tiers fundamentally without any restriction. And then on top of that, if we want, we can add TSVs or C4 connections, just connecting this element to the upper one. Again, you see that the key message is that if we are using this technology, we have a very high degree of heterogeneity. So what is our goal? Fundamentally, our goal is to try to understand, to try to model the electrical characteristics that we have in this kind of monolithic implementation connected by MIVs, to have a look to our system and to try to see if we can connect elements that, for example, are in the upper and that then have to be connected to the lower vias using a set of optimized wire structure with the optimal number of buffers. And in addition to that, taking into account that for the connection, let's say from the memory to the lower tier, we can use this small block that we have in green, this decoding logic to interpret the values. If we think in terms of the transmission of data, in principle, you should say what I need is an encoder for the upper part and then a decoding in the lower part. It turns out that in a lot of scenarios, it is possible to encode the information already before saving it into the memory in such a way that actually the only overhead that we have is to do the decoding. So then our challenge is how can we determine the optimal number of repeaters and buffers that we have in our interconnect? How can we determine which is the part of the wiring that should go in tier 1 and in tier 2? And finally, which is the optimal low power coding that we can use to try to decrease the energy to the maximum. In this slide, you get just one example of the kind of heterogeneity that we are analyzing. We want to develop a methodology that allows us to study different technologies and to model different technologies, making sure that even if we have some changes in the technology because of some, let's say, improvement in technology, that nevertheless our methodology will be able to capture that. Because of that, we are analyzing a a very broad set of technologies, probably broader than actually what you can find in reality. In terms of the bottom tier, we are assuming that we have technologies that can go from the equivalent to 3 nanometers to the equivalent to 18 nanometers. In terms of resistances, you see that we are ranging the resistance of the wire from 77 ohms per micrometer when we are using a very dense technology, 3 nanometers. And then if you are using, let's say, older, more classical technology, for example, 18 nanometers, then we are assuming that then the resistance will be slightly better, 23 nanometers, 23 ohms per micrometer. In terms of a capacitance, the variation is slightly slower. In terms of coupling capacitance, we are ranging from something like 60 attofarad per micrometer to something like 51 attofarad for micrometer. We were also modeling the ground capacitance, where actually we have some changes. And you see with that, we can already get a broad spectrum of, let's say, typical scenarios. In terms of the top tier, we are assuming that the technologies are older, and fundamentally we are using technologies ranging from 7 nanometers to a very, very old 65 nanometers, probably much older than what you will get in the praxis. And again, we are modeling the resistance and the capacitances. You see that this time the resistance, the values of the capacitance that we get are slightly better. We are assuming that in the top tier, we have a wider set of interconnect and that the interconnect are actually better. We did for parameters. The first thing that we did is just to do 3D simulations. So 3D in the sense of simulations in the 3D domain so that we can characterize the resistance, inductance, capacitance of all the interconnect in all these technologies. Once we have this model for the wire, we were just fundamentally looping all over all the scenarios in terms of the separation between metal lines, the width of the metal lines, and the strength of the wires. And for that, we were calculating the energy consumption that we have in the different configurations. In the slide, you can see as an illustration a configuration where we have only in one tier, but obviously we did the same simulations when we go from one tier to the other tier. If you try to simulate just one interconnect in one single wire, then actually the number of simulations is relatively simple. In our case, since we want to understand low power coding, we were actually simulating the delay and the energy consumption that you get when we are sending any pattern of 4 bits through our extracted interconnect architecture. So we were simulating something like 6,000 scenarios per every case. We wanted to compare this, let's say, empirical data with the mathematical model. And for that, fundamentally, what we can do is just to try to analyze how can we model the energy consumption in an interconnect. This is a classical result where you are in 2D. Fundamentally, if you have two lines, then the switching activity of one of the line versus the other one produce an energy consumption. The energy consumption is fundamentally the integral of the voltage, which is a constant, times the current, which has a very strange shape depending of the nonlinearity of your CMOS technology. Remarkably, when you try to calculate analytically this result, actually you can calculate a closed formula. So this VDD squared Ci j multiplied by the bit in the line K and multiplied by the variation of the BK minus variation of the bit cut. And this formula actually agrees extremely well with the simulation result, even if you have more than one aggressor, even if you are in a scenario like TSVs where you have more than one line, which are, let's say, adding one coupling capacity. You can try to reduce the formula even further. You can see that fundamentally the energy consumption that you get is proportional on the one side of the factor CII, which is related with the ground capacitance that the interconnect in 2D or 3D is seen. And then we see IJ, which is the coupling capacitance that the interconnect is seeing between two neighbors. From the point of view of the data that we are sending, the fundamental factor that we have, it is increment BI squared, which is fundamentally the probability that we have some change in the information that we are sending. And then the second factor is the increment of VI squared minus the multiplication of increment of VI with increment of VJ. This is fundamentally the coupling capacitance between these lines. This formula set is extremely precise, even for 3D, assuming that the lines, the information that we are sending is aligned. If you assume that the information that you are sending is completely unaligned, then actually, again, you can do the same mathematical analysis and you see that you get one formula that actually is even simpler. It just depends on the square of increment of VI. In reality, the problem is that the signal get disaligned as they are transmitting, as they get propagated. If you use the classical formula to try to get the energy consumption with alignment, you are going to get MSA, which is extremely good. If you try to do the same analysis for the case of misalignment, you will see that the MSA is getting much, much worse. In this case of the simulations, was something like 10 E minus 5 Joule square of degradation. If we want to improve the accuracy, even in the case of misalignment, what we can do is to add one term here, the term capacitive misalliance multiplied by T misaligned, that fundamentally model the effect of the variation of the energy when the patterns that propagate through our bus move over time. Just adding this additional factor decreases the accuracy, or decreases the error, increases the accuracy by something like a factor of 10. In this result, you can see in a 3D plot for all the scenarios that we were analyzing, just which is the value that we were getting for the ground capacitance, for the coupling capacitance, and then for the misaligned capacitance. The two key observations is that you see that there is one region where actually the error is slightly larger, 7 even 5. You have other regions that Aachen was that actually the MSB is smaller. So obviously there are some situations with misalignment is larger, where error is slightly larger, but nevertheless with a quite, let's say, small range, quite accurate. But the other thing, which is even more interesting, is that there is a very strong correlation between the value of the misalignment capacitance and the CC and CG, so that it is almost possible to try to determine the optimal misalignment capacitance just as a function of CC and CG. This implies that probably it could be possible to produce a much more accurate model for energy consumption if we are using a principal component analysis technique. So what we did is, in addition to the traditional terms of the ground capacitance and coupling capacitance, we were adding another term, T3, that was calculated as the PCA of the result, and then 1 through 3, which is the effect of that. And you see, with that, we get one model that fundamentally had the same complexity that the standard model with the misalignment effect, but that produced one error, which is even smaller. Moreover, the advantage of this more precise, let's say, formulation is that it allows us to understand which is the energy as a function of the factors T1, T2, T3. And these are exactly the factors that we can reduce through coding. Once we have understand our technology, our next step was to try to understand the data. As an example, just because of the, let's say, the relevance today, what we did was to take the data regarding the activation and the weights that we have in different modern machine learning applications. For example, we were using a visual transformer a swing visual transformer, and an OPT machine learning approach. We were taking the data regarding the weights, the data regarding the activation. So fundamentally, this will be the data that we saw in the previous slide, in the previous presentation, that we have to move from the memory to the hardware accelerator. We were analyzing this data. We were just calculating the typical standard deviation, the entropy that you have in the MSPs. And we were realizing that actually there was a lot of redundancy in the data. So you see that the entropy in the MSP is actually much smaller than the number 4. This means that there is a large potential for improvements in terms of low power coding. Our next step was to develop one hardware architecture that was allowing us to implement different low power codings. Maybe we can discuss that later, but fundamentally in terms of low power coding, the approaches that produces a better trade-off between complexity of the encoding approach and reduction of the transition activities are the traditional K1, K0 low power coding approaches, yeah, maybe together with the presence of a correlator. So what we did was to develop one hardware module, here you have it, that can be configured so that it can implement different low power techniques. We implemented the module in such a way that we can reduce offline the number of configurations that we have. For example, we can decide offline that we don't have the possibility of a correlation, while keeping the possibility of the inversion and the K0. Or we want to develop another hardware that, let's say, have all the possibilities, or we just want to restrict ourselves to the possibility of sending the normal data and just to allow the configuration 0 to have a K0 coding. With that, fundamentally, you can see that you can get a trade-off between the area overhead in the encoder, the energy of the encoding process, but then the total amount of the reduction in transition activity that we can get. Our last step was to analyze how much energy could we reduce in terms of the movement of data as a function of the data that we are sending. We were using fundamentally all the data that we have in the previous transformers, and what we are representing here is just which is the topology in terms of coding, which is producing the best reduction in terms of energy as a function of the coupling, ground, and misalignment effects. The first, let's say, remarkable result is that there are some combinations of scenarios in monolithic 3D where actually no coding was producing the best result. There are other scenarios where actually K0 is producing the best result. If now we move to another kind of data, you see that for this case, where actually the correlation in the data is fundamentally changing, then again, we have a couple of points in orange. This is where the point where no coding was actually working better. And then K0 with a normal correlator was actually the approach what was producing the highest reduction of low power coding. You notice if you compare the two approaches that here and here, yeah, we are getting always a different optimal low power coder. Again, we move to another scenario, we just change another kind of data, and again, we get a combination of optimal low power coding technique, ranging from no coding in orange, the K0, which has a very large range of a scenario, which is the best coding. Then we have also a couple of points with K0 with the correlator, and a very small set of points with K0 and the inversions of the lines. Good. Then finally, when we take all this information into account, what we can do is just to analyze the typical data that we can that we have in our calculation, we can take the particular 3D scenario that we have, so the combination of 3D technologies, and with that, we can select the low power coding template that is producing the best result. How much energy can we use with this? So how much energy can we use if we select this optimal low power coder? Here you get the result, and you can see if we compare for the different scenarios, the case of no coding with the case of the best coding that our approach produces, we get improvement that range from a factor 3 to a factor 4.6. It means we are cutting by 3, we are cutting by 4 the power consumption that you are dissipating in the interconnect. And the price for that is just a couple of XOR gates put in a clever location. In the next slide, we are just analyzing what is the potential in energy saving that we can have when we use a standard approach like K0 versus the best coding approach that we can configure with our result. And if you see that if we do coding, we get a factor of 4 in gaining, but if in addition to that, we try to use the best coding let's say, associated with the data that we are transmitting, then we can get something like an improvement in the energy consumption of something like 2.3, something like cutting by half the energy consumption. Okay, there are other configurations depending of the particular 3D technology, where you see that actually the reduction of K0 versus the best coding is relatively small, and these are just the cases with coding with the traditional K0 that we were developing in the past is actually so good that there is no way to improve it. So summary, what we have seen right now, we have seen that it is possible with a very small amount of hardware to reduce the power consumption when we transmit data in heterogeneous monolithic 3D technologies. We can see that we can develop one configurable encoder where we can feed the coding approach to the kind of data that we have in our application. And in addition to that, we have seen that we can model the energy consumption in 3D technologies just using an extremely efficient PCA approach. With this methodology, we see that we can more or less produce a saving of a factor 4 in terms of the energy that we need for transmitting our result. I think with that, maybe I can conclude this part of the talk. So thank you very much for your attention.
Yeah, thank you, Alberto, actually, for the talk. So I think we can move to the Q&A section of the part. I think I see two questions in the Q&A. So the first is for the first session. Are there any effective schedulers that you have tried to, I think, to minimize the aging effects? Anuj, I think you're muted.
So we just tried the standard schedulers, which we can find in the literature for normal multi-core processors, and then we just got the results. We just assume the normal schedulers doesn't really care how many active cores are underneath, so we have tried to. I mean, they do not specially optimize for the core failure resistant multi-cores, but they can continue to operate like on any other multi-core even with a failed core. They just assume that the underlying microarchitecture or the number of cores have changed. We specifically did not develop any, try to maximize or optimize the reliability for these kinds of multi-cores using a new scheduler. We have not explored that yet.
Okay. Thank you, Anuj. I think the second question is for the second session. In the combined loss function, why is the position loss multiplied by 10 and why prioritizing the position of error over the temperature error? I think it's for Tahani.
Yes. Actually, when we talk about like two different factors or two different set of parameters, and one of them it's like change very fast because as we said for the position, the model go through like 4 layers, but when we talk about the temperature, it's go through 1 layer. We expect to have like very fast change on the position, and we need to consider this as a factor to not averaging them equally. We try to give more attention for the very fast change on the parameters related to the position.
Okay, and I think the second, I think there was a question, the question was why is multiplied by 10? Is there any?
Yeah, it's multiplied by 10 to give more attention for
Okay,
the fast change on the parameters that related to the position, because this is considered a weighting technique. Weighting when we want to give like more like impact for specific factors, because we expect it change very fast compared to another one. So the weighting, it's a technique to pay more attention.
okay, okay. Thank you very much, Tahani. And I think there is also a question for Alberto. So, what would be the future for this framework? Would be to check a new system or enhance the methodology for a more detailed analysis? And what could be the optimization methodology to exploit the results of this analysis?
So fundamentally, the idea is, let's say we are implementing, for example, a machine learning accelerator in 3D. Then fundamentally, we could first characterize the particular 3D topology that we have. With that, we can calculate the coefficient CMEs or the ones for the PCA. And then out of that, we can just immediately obtain which is the optimal encoder that we need for the application. So in our VHDL code, we just need to add this additional XOR gate. And with that, automatically, we will be reducing by 4 the power consumption that we have in the transmission of data. For example, when you are loading the weights from the memory into the hardware accelerator. So in terms of, let's say the methodology is extremely simple to use. The only thing that requires some effort is the first characterization of the equivalent physical capacitances. And for that, we need to do some, let's say, finite element simulations to characterize the propagation of the information through the wires. But once this is calculated for a given monolithic technology, then actually the modifications in the VHDL code is just to add one module with a couple of XOR gates. So extremely simple.
Okay, can I ask one more question about that? Would be beneficial also, there are some applications that, let's say you can, let's say reduce the least important bit or try to approximate some bits since they're not so very interesting.
Yes, even more. So actually, when we are working in, let's say, machine learning applications, it turns out that all the bits are not equally important and all the weights are not equally important. So if you want to, let's say, encode your data and you assume that there are some cases where you don't need to have exactly the same value, that you can have some losses in the LSVs, then the potential that you have for low power encoding is even larger. And then because of that, the gains are actually larger.
Yeah.
In this particular case, we were restricting ourselves to a low power coding that guarantees 100% accuracy. But if we reduce that a little bit, then suddenly the gains are even larger.
Yeah.
And actually, we are also exploring in another project that, and yeah, it's almost factor 3 larger.
Yeah, exactly. It would be very interesting.
Exactly.
Exactly. Thank you, Alberto. So I think we have passed our scheduled time by 5 minutes, so I think there are no more questions. I think we have to thank our speakers and for joining the event and giving this talk. And we can conclude the webinar. So thank you, Alberto, Tahani, and Anuj for the talks. Thank you very much.
Thank you very much for the invitation, and then see you soon.
See you soon. Exactly.
Okay, thank you. Bye-bye.
Thank you. Thank you, Anuj.
Thank you very much. Bye.
Yeah. Thank you all. Thank you.